hopefully everything works. You see my screen in full presentation mode? Yeah?
Yeah.
Cool, perfect. So as you mentioned, I'm gonna talk about operational monitoring of rock glacier velocity and the way we do it in the PERMOS network. So that's a work, as you can see on this title slide, that's a work that is not only done by me, but really by the whole scientific committee and members of PERMOS in Switzerland. You have all the logos of the institutions, except for one, I guess. One is missing, University of Innsbruck, who's newly a member of the PERMOS network. So yeah, this is really a summary of what happened in the PERMOS network since about 15 years. But to start, just a brief introduction about rock glacier velocity. So probably most of you know what it is. So that's what we try to define within this RGIK action group. And then the idea about rock glacier velocity, why we want to measure it, is because we saw that there is a similar regional evolution of rock glacier velocity, which actually strongly depends on the ground temperature changes. So basically what we can say with rock glacier velocity, we can provide information about, indirect information about the permafrost temperature and the permafrost evolution. And this is also why rock glacier velocity has been accepted as a new associated parameter to the ECV permafrost in 2022. So that's also a summary of the work of this action group. And then now rock glacier velocity is included in all these documents that you see here. So that's the GCOS implementation plan, the GCOS ECV requirements, and the GTNP strategy and implementation plan. And what's actually included in this document comes really from the action group and has been put into 3 different documents. So we have baseline concept with definitions, we have practical concept and technique specific concepts to actually help with the measurement and standardizing the work of collecting rock glacier velocity data. And what I will show you now, I will talk really about PERMOS, so what we do in PERMOS. So for those who don't know, PERMOS stands for the Swiss Permafrost Monitoring Network, and its overall aim is the collection of long-term baseline data documenting the permafrost state and changes in the Swiss Alps. So here you have a map of all the sites. We not only measure rock glacier velocity, as I will show you later, but mainly also ground temperature, where we have about 15 borehole sites, 22 ground surface temperature sites to capture really the diversity, as you see on this picture, of the alpine environment. So rock walls, talus slopes, rock glacier. We try to cover everything as much as we can with different exposition, elevation range, etc., etc. And in complement to ground temperature, we also have ground ice content that we measure using ERT monitoring, so geophysics, where we do once a year measurement of electrical resistivity. And then finally, we have a measurement of permafrost creep velocity. So that's 18 rock glacier in total with 8 permanent GNSS device. So rock glacier velocity in PERMOS, it's actually started since about 2010, has been measured systematically at these sites that you can see here. So as I mentioned, that's 18 rock glacier in total. And the overall aim is to really measure long-term monitoring, so long-term data with the same method and consistently. And we focus on annual displacement rate with 1 measurement a year at the end of the summer. And then recently we added permanent GNSS to our monitoring strategy to document the seasonal variation of permafrost creep. And these permanent GNSS, they complete actually the TGS data that we have, so they are installed on the same sites. In order to have really consistent data and to compare what we are actually measuring, we need to have a similar approach at all the sites. And this approach, this operational monitoring, goes in several steps. So the first one is the monitoring setup, how to select the site, how to design the surveys, and then we have the measurement, which method do we use, how do we use it, how is the maintenance done, and then the raw data. So can we, how do we, which format do we use, how do we check for data completeness, and then the pre-processing once the data are collected, how to control the quality, to calibrate, to correct if necessary, and then we archive these data in a secure database with open access to the data. And then finally, we have some processing steps to produce graphics and standard outputs. And for all of this, in order to have all these steps consistent, we need quite a lot of documents and standardization tools. So this is just an example of what we do within PERMOS. So and I will go into detail now in this presentation for all of these different documents. And with really, again, the aim to generating long-term standardized rock glacier velocity in a climate-oriented perspective. So the first part of the standardization process starts really at the measurement level when you choose the site and when you do the measurement. And this is done by using the same measurement best practices. So it's to provide a guide how to collect the data, to produce comparable data for many different landforms and ensure consistency. And how we do it in PERMOS, so we are in the process of doing it. This is not a done deal or a finished deal, but we are now, based on the last 15 years of experience, we are writing down a sort of manual how to concretely measure the GPS point, the location, and to gather the data. This only covers the measurement part and the maintenance, so the survey design, the site selection, the network setup, and the measurement, but it doesn't yet cover the processing of the data. And this work is actually, we have something ongoing in PERMOS, but there's also something ongoing on within the RGIK community, and this is also something that is currently being done by the Global Cryosphere Watch in this best practice guide to monitor permafrost. So there will be a small section about rock glacier, but not so specific. So once we have this measurement best practices, so then we go to the field, and then there is a very hard work to do to actually collect, to document what is done in the field, and to do so systematically and for a long time period. And what we are using within the PERMOS network is a systematic standard fieldwork logs that look like this, where you can actually enter the survey operator and instrument, the dates, and all the information. Every time you go in the field, you fill one of these, it's a one-sheet formula. And then you have a small section about the description of measurements. So we are measuring in situ. So we are measuring point coordinates for always the same sets of points. And then you can say, okay, which point did I measure? Which point did I not measure? Why? Is it something that we should do? Should we replace this point? Or is it just not enough time to measure? This kind of things we can document in this. And then there's also some information from the people in the field to the people then doing the processing. They say, okay, this we can name a certain set of control points, so not moving points that will serve then to correct the locations and correct the data. You can also give reference points, like the best points, the most representative, if you wish. So this information are then transferred to the person who does the processing together with the data. So once the data and the metadata are collecting, we need to check the data. And for this, we develop a semi-automatic tool that actually takes into account the already existing data from the preceding years and then compares it to the newly collected one to identify if there are missing data, if there are wrong data, or if some correction are needed. And the way it looks, it's a bit small on the screen, but basically we enter our data file and then we have these three tables. So there's the first one is the new measurement of already existing points. That's perfect. You can see what's happening. The second table is like existing point that were not measured. So you have the list. And the third table here, there's nothing, but if you measured something new that year, then you will also get an information. And in addition to this table, you get also standard plots of trajectory. So that's the first one on the left. And then so you have east-west, east-north coordinate, and you see the trajectory of your point in the planimetry, and you can check if there's a strong deviation or if something is happening. And then the second plot is horizontal displacement versus elevation change. And there you can also identify problems within your measurements if there is. So in this particular example, there is not, but in this one, there something happened. So you have a shift in the trajectory and also a large drop. So probably a boulder turned or fell somewhere on the rock glacier. So then you can flag this data and then go on with the processing. And these data and all this information are stored within a secure long-term database. So we have one database for all the measurement and all the data within the PERMOS network. So it's not only rock glacier velocity data that we actually store, but also borehole temperature, ground surface temperature, and geophysics information. And the way it looks like, so there's a whole section about metadata. So there's the site information, where it is in Switzerland, when it started, what's the landform, the lithology, and whatever you can ask for. And then there's something specific to the rock glacier. So what is the rock glacier name? When did it start really the rock glacier velocity measurement? And then there's something about the survey and the points. So all of this is the metadata, and then you have the data itself. We only store position data. We don't store velocity data. And then we have some standard codes to actually compute velocities and do the output results. And then finally, so now we have many points stored in the database, but we still need to do some time series. So basically, what a typical site would look like is what you have on your screen. So you have a rock glacier with all the red dots are all the measurement points that we are actually measuring the position every year. And then for this, you can calculate velocities. So that's just 3 selected points on this landform. And you can see there's a large variability. If you do the same plot with all the points, it looks like this. So it varies from 0 to 5 meters, depending on the point. Obviously, we are not using everything to assess the velocity of rock glacier. One other way to look at it is in relative terms. So each time series now is relative to its mean, and now it looks a bit more clear, but still there are some selection to be done. And this is a bit the standard processing, so that what comes after the data are stored in the database. And this is really the work that has already also been performed in the action group to understand how to select the points, why, and how to compute the mean. So I'm going to show you our way in PERMOS, which is a bit different than what the RGIK suggests, but not so different. So the first step to actually select your points is we use the homogeneity of movement within the landform to actually identify time series or potential time series. So in this case, we have these 3 zones that are more or less uniform. So the movement is going the same direction with almost with the same evolution and amplitude. So it looks like this. So you have, again, these 3 colors, and you can see that the 3 zones can be homogeneous, but they're also very different from one another. And then now the question is, okay, so if we want 1 time series per rock glacier, which one do we choose? Do we choose the green one, the blue one, or the yellow one? It's up to us. And then for this selection of the zones, we focus on several parameters. The first one of it would be the climate representativeness. So we need a zone that is actually not disturbed by local factor, such as topography or margins, or depending where you are on the rock glacier, there are different factors. And then another very important point is data quality and completeness. So maybe there are zones on your rock glacier that you can measure only once every 2 years, and then you have a lot of missing data. So that's probably not the optimal place to select your points. And then there is also the long-term perspective. So as you can see here, there's one zone that is very near to the front, and then this one to measure on the long term is probably not so easy. although the other two are probably a bit safer over the long term. In this case, we actually chose the yellow area in the end as our time series for the rock glacier, and this is what it looks like if you compare it to all the data now that are measured. And there's a second thing that we also have to take into account in the data processing is the time series consistency. The question here is, again, for these 3 points, you can see they vary in displacement between 15 and 65 meters in 20 years. But then the question is here, how to monitor rock glacier moving in several meters per year over a long time period. So 65 meters in 22 years. So if it continues in that direction, then in 22 years, the points are outside of the landform. And then the question is, are we still measuring the same thing? How do we ensure the consistency through time? And this is even more difficult than the spatial heterogeneity. But what we actually do is a regular quality assessment of the signal measurements. We adapt regularly also the measurement used for the site average. So maybe in the first year we were only taking points in this area, but they moved quite a lot. So now we changed our average for maybe higher up, or we're replacing points. That's also something that can happen if you start losing your points, or they are actually rotating and you cannot measure them. So you can also replace points, which looks like this. There could be no overlap if you didn't catch it early enough, or there could be overlap. And then at that point, you can compare the velocity, which in this case fits very well. It's not always the case, but it's always nice to see that. And now, I guess for the results, so that's a bit how we do it in PERMOS. And now I will show you the results of the different techniques, starting with the seasonal evolution that we actually measure. So there's in total 8 permanent GNSS. I'm just showing an example of 3. But what you can see here, it's for 3 very different landforms in different places. But you can see in all cases, you have this typical winter minimum, end of summer maximum, and then the start of summer snowmelt acceleration. And this is very typical. It's found for almost all landforms. And you can see this pattern repeating from year to year. And also it's the relative variation are independent from absolute velocity and velocity trends. So meaning every year, even if it's slowing down, you will still have this pattern, as it's the case, for example, in 2021, 2022. If we go for the interannual results that we have within the PERMOS network, so that's a bit more sites. So this is what is shown here. You can see that almost all the landform are following the same evolution. They have marked interannual variation, but nevertheless similar observation at most sites. There are some atypical behavior that are not shown here, but you can see on this graph. So this black line is exactly the same for the 2 plots. So this is the first one is the plots with the rock glacier that follow the same evolution. And in this second one, you can see it's actually 2 rock glacier. There's one that is sort of stagnating in terms of velocity, almost decreasing, and one that is strongly accelerating that falls even outside of the plot. And this is 2 zones on the same rock glacier that are completely different. So that we have, in this case, a destabilized rock glacier that is accelerating, and that is not in line with the climate or the observed ground thermal conditions. And this is the same here. This is also not in line with the ground thermal properties, which are actually warming, and you would expect an acceleration of the rock glacier. And this is exactly what I just mentioned. So the rock glacier creep velocities, they are related to ground temperature change. So as you can see, here is the same graphic as before, and down here is the ground surface temperature. So it's a mean over 2 years measured at the location under the same rock glacier. And you can see that the evolution is sort of similar with decreasing ground surface temperature when you have decreasing velocity when you have decreasing ground surface temperature, and increasing when you have increasing. So this is the case for Switzerland. So these are the results from the PERMOS network, but I want to finish on this. This is not only something that happens in Switzerland, and that's something that is actually valid pretty much everywhere. So this is a study that was done. So where we compiled data from the European Alps, the dry Andes, and Central Asia. And as you can see, in all the places you have this acceleration with warming climate, and hopefully soon we will be able to actually have more regions around here and to complete this analysis. So these are done using photogrammetry for the two last region. Maybe we can complete this with in situ measurement and interannual observation to go a bit more into detail about this trend. So final take-home message, rock glacier velocity evolution is related to ground temperature change. And in the Swiss Alps, interannual and multi-decadal trends are observed. There's operational long-term monitoring of glacier velocity is feasible. So I showed you here an example for in situ measurements, but this could be also achieved using remote sensing techniques. Although it needs quite a lot of documents and procedure to standardize the data from start to finish, so from the measurement to the final product. And this is an ongoing effort within the IP action group. So, okay, it's not an IP action group anymore within the RGIK community that will continue. And then finally, rock glacier velocity provides information on the impact of climate change on mountain permafrost. And then hopefully the goal now is to provide worldwide data using remote sensing data, for instance, INSAR, but also aerial images and satellite images. And on this is my final slide. So I will thank you for listening to me and open for questions.
Bravo. Thank you, Cécile, for the presentation. That was clear, sharp, and updated, state of the art of rock glacier velocity. So yeah, the room is open for questions to Cécile, even on the chat if you want to write them, or just raise your hand in the app. So have questions or comments to Cécile's presentation? Was super clear.
Or too fast.
Or too fast. Questions, so I can have, Jan, of course. Hi, Jan.
Hi, can you hear me?
Yeah.
Yes.
Yeah. Hi, Cécile.
Hi.
Thank you for your talk. Very informative and clear. I have one question. May I ask how much does it usually cost to set up a permanent GNSS station on a rock glacier?
That's a very good question. I would say for permanent GNSS, it's definitely more expensive than a terrestrial survey. So for the terrestrial survey, I can tell you it's usually what we do is 1 day of field work for per year, and then you just have to go in the field. And then in terms of processing, it's also pretty fast. For the permanent GNSS, I think Jan is in the room, so probably he's much more aware, but it depends strongly on the type of instrument that you're using. So maybe Jan, if you have a...
I was already expecting you pass this on. Yeah, so the instrument itself today is really a standard commercial GPS receiver with. It's good to have a better active antenna, but really this is something that's costing a couple hundred. But packaging it, making it weatherproof, and setting up the whole service, of course, is the big thing. So if you just do one station, expect to pay or expect to have anything ready between 5,000 and 10,000. Your favorite currency. if you, like we did in a early pilot project, we did a batch of 30 stations. Then I think about 1,000 per station per year is rather reasonable over the whole cost. But really, the most of the cost is the field and office work in the background for all the processing. So all this processing and homogenization that Cécile mentioned, all this processing chain, and we are in discussion now for 10 years to consolidate on a data format and a standard data product and these procedures, and we haven't reached that. So that's the long part of my answer. Yeah.
Okay, thank you. Thank you for your answer.
Do we have another question for Cécile from the public? Comments, suggestions? Otherwise, I think I have a question for you.
Yes.
Just I wonder, like in the case of when you replace a point that is missing, especially in the front end, then you need to choose if these points was the end of the life of the point because it arrived to the front and then it fell. So what is the point to replacing that point if you need to go back to the original point, or you put it nearby the front and it will fall again soon? So what is the criteria behind replacing those points?
Yeah, that's a good question. It really depends why you're replacing your point. So sometimes it's because the boulder is simply rotating on itself, and then maybe you cannot measure it anymore, or then in this case you would try to look for a boulder very near that probably doesn't do that, or even on the same boulder but behind. But in the case of front, which is actually the most often the case, then what we usually do is we go a bit further back to avoid exactly what you said, to have this actually replacement point fall after 2 years. So that's not very useful. So in this case, it's very difficult. So we try to do the replacement before we have the boulder falling, so we can have a few years overlap to understand what is actually the relation between the new point and the old point. So what we try to do is to follow back the trajectory that the initial point followed, and then to start back again up from this point. But this is very tricky, and also in terms of computing velocities and processing, it's still sort of, we haven't done like a rigorous study on exactly how to do that. So it's really like a problem that comes up more and more now. So that's why I showed it. But at the moment, we still try to avoid having this replaced point in the references that we calculate the velocity in.
Just one complement to your answer. I guess because the measurements are done in a Langerian system, no? You follow the flow field as it's not Eulerian, that is fixed to the space and time.
Yeah.
But do you expect some disagreement if you change the methodology to some Eulerian? Because at the same time that you move the point, you're guessing that that point represents mostly an area that is fixed, I guess, or an area that is moving with the rock glacier. So do you think that there will be some kind of inconsistency between both measurements in the long term, especially in terms of acceleration?
Yeah, I think it would be very interesting to try actually to do this, to perform this analysis. Also because some methods, as you know, use also the Eulerian or the Lagrangian. I mean, to compare with different methods would be also interesting to do this analysis. I'm not actually sure if we have the density of point that we can do that using the GPS points that we have, but it could be something to try. And I would expect not so much difference, except at one point, depending where the points land. So as long as the movement is, because you can change a zone that accelerates, there are faster, slower zones. So at one point, if a point goes into something different, then maybe you have this change. That's a very good idea for further analysis. I think there's one question in the chat.
One question.
So I can read it.
I can read the RGIK. What is the potential of ground-based instar GB instar for rock glacier RGIK measurements?
That's a very good question. I'm really not INSAR specialist, so I would be very difficult for me to answer you. I would guess that for ground-based INSAR, it's probably the same potential as you have for any kind of remote sensing, like if you do drone or if you use close range remote sensing, then you can be really precise and you can have any kind of velocity that you want. Compared to satellite-based INSAR, this is very limiting. So there's only a certain range of velocity that you can actually detect with satellite-based INSAR. So I would say a ground-based INSAR should be used only for those rock glacier that you want to see monitor that are outside of this range and for special cases. But I'm really not a specialist, and I'm not sure if there are specialists of ground-based INSAR in the room. So maybe that would be an open question for the public.
Yeah, Lynn is not joining us today.
No, but Jan, maybe, I don't know.
I think Lynn was working with some ground-based INSAR for landslide monitor or something else, but yeah. And the next question is from Robbie. Thanks you for the presentation. I want to know, are there any correlations between rock glacier velocity and external factors such as climate change or local environmental conditions?
So that's the first part with the relationship between rock glacier velocity and climate change. So in terms of, I guess you're talking in terms of air temperature, increasing air temperature, then this is really what we try to show with this global study or with this action group. So to find this link between rock glacier velocity, ground surface temperature, air temperature. So to do this link. So also with permafrost temperature. And as for local factor, definitely there's a link, but it's not always the same. So we have these cases of destabilized rock glacier where there you have strong acceleration that are not due to increasing temperature and that are really due to local mechanical topographical factors. So there's also water that plays, we think, a huge role in terms of velocity and variation, but that we still don't understand. So these are really very good questions, research questions that are, I think, being researched at the moment by the community. So this is something that we also go in the direction of within PERMOS. Hope I could answer the question.
Any other question or comments to Cécile? No. So I think we can just close the seminar for today if there's no more questions. And I want to thank you again to all of you for attending the seminar and being active in asking questions, and to Cécile for willingness to present the work of rock glacier velocity in PERMOS.
Thank you.
And just remind you that the next seminar is for the moment cancelled. Francesca Bearsot is not able to give the seminar in September, but you will be informed by the email list promptly. So thank you again, and hope to see you in October for the next seminar.
Thanks, Seba.
Thank you.
Ciao.